Good afternoon, everybody, and welcome to today's technical webinar. This is our first one of 2023, and we're excited to bring you a nice lineup for the next 11 months. I'm your host, Jessica Bennett. We're very excited for today's webinar that will be presented by Dan Griffiths and Brian Vanderglass on an off-site permeable reactive barriers and on-site residual source control, a holistic low-cost solution to a 1-2 DCA problem. A few housekeeping items to start off with. All phone lines will be muted until the Q&A session at the end. If you have any questions throughout the presentation, you can either submit them in the chat feature, or you can hold them until the end and ask either through chat, or you can raise your hand and we'll call on you. This webinar has been approved for 1 PDH credit. If you'd like to receive credit for attendance, you can download the attendance form. We'll be posting that during the webinar as a web link. If you have any issues downloading that form, you can send us an email to daniela.savin@parsons.com and we can send you that form. And if you miss any of the questions or the answers, this webinar is being recorded and it will be available on our YouTube channel the next few days. Next slide, please.
Yep, can you see the next slide?
Not yet. So I guess there might be a delay.
Yep, a little bit of a delay. How about now?
Yeah, okay, I see it now. Thank you. So quick agenda, we'll introduce both our guest speakers today. They'll give a core value moment, and then we'll get into the technical presentation and wrap up with questions and answers at the end. Brian Vanderglass is a senior project manager at Parsons. He has over 34 years of experience in environmental restoration. He specializes in contaminant investigations and remediation projects, and he's a professional geologist. Dan Griffiths is Parsons' Emerging Contaminants Practice Director, as well as the Subject Matter Director for the Groundwater Restoration Practice. He has 26 years of experience, specializing in complex environmental site investigations and remediation. He's also a registered geologist and a Parsons Fellow. And with that, I'll turn it over to Dan for the core value moment.
Okay, thanks, Jess. So Parsons has 6 core values, and we like to start these presentations by highlighting one of them. In this case, I'll highlight innovation. So at its core, Parsons is as a technology company. Much of our business is in cybersecurity and missile defense, military intelligence, etc. And we like to bring that kernel and core of creativity and innovation to our other business lines, including our horizontal construction business, which is roads, highways, and bridges, and our environmental practice. So for environmental practice, we're really recognized in the industry for innovative approaches to complex projects. We try to bring technology and innovation to a project to improve, the performance of our remedies and to reduce costs, both short-term and long-term. And we possess a pretty substantial resume of notable first-of-a-kind, one-of-a-kind applications for difficult projects and difficult contaminants. We were really on the forefront of the monitor natural attenuation craze in the early 2000s, really catapulting those learnings into phytoremediation, enhanced biogeochemical transformation as remedial approaches for challenging sites that are cost effective and are performance effective. And finally, we have a research and development lab in Syracuse, New York, where we do a lot of our own internal research and development to develop new technologies to fill the gaps in the industry, particularly for emerging contaminants like PFAS. And we also do a lot of treatability studies for our clients to demonstrate that the innovative technologies that we are proposing are effective for our client sites, site geochemistry and contaminant conditions to prove performance before we get into the field for the full scale. At the center of the slide, you'll see just a couple examples of recent innovative projects that we have completed, ranging from a 1,4-dioxane site in South Carolina, where we're applying phytoremediation and aerobic biodegradation as the final and full-scale remedy for that 1,4-D site. And we have an example in Northern California where we closed a former plastics plant using enhanced biophytoremediation, zero-valent iron, and monitored natural attenuation. Also a site up in Galena in Alaska, where we're applying in situ remedies to degrade contaminants remaining from when that facility was an Air Force base, so that we can turn that site over in a clean and pristine condition to the new users. All of the examples focus on in situ remedies, on new but proven technologies to implement remedial solutions that are better performing and ultimately lower cost. And over on the right-hand side of the slide, you see a couple of our patents that are relatively recent. We'll start on top with the methane biofilters technology that's patent pending, and it's an innovative solution to leaking methane wells. That could be a natural gas well that was abandoned, or a vent at a landfill. So that's a great technology that we've been working on for some time. Hodisco is another great example. It is the first full-scale technology capable of degrading PFAS in situ. Hodisco is somewhat of a misnomer. It's really a combination of chemical oxidation, metals-based catalysts, and a slight heating, usually 5 to 10 degrees C from ambient to affect destruction of those PFAS compounds. So Parsons is focused on innovation, not just in terms of our cyber intelligence and cybersecurity, but also in terms of bringing better solutions to our environmental clients, such that we can perform and close sites more effectively for our clients. And from there, I'll pass it over to Brian for the first half of the presentation.
Thanks, Dan. As the project manager for this project for the last 2006, I like to think that we applied a number of those different technologies, and I think you'll see this as we go through this, that we had to be creative and flexible as we move through. So I'll start talking about the overview of the project. This presentation reviews the decade-plus efforts performed to address a dissolved phase plume of 1,2-dichloroethane and the subsequent characterization activities completed to provide solutions for the source area. The contaminant of concern is really only 1,2-dichloroethane. It's a manufactured chemical used in plastics, rubbers, synthetic textiles, cosmetics, solvents. Has a groundwater protection standard of 5 parts per billion. It's also the only contaminant at this site that actually migrated off the site property. And it's really the only contaminant of concern that when we're dealing with the agency trying to achieve closure. The aerial on the right of the slide highlights some of the challenges with regard to affected property ownership we had in this project. And that affected property ownership played a large role in the development of the integrated approach. If you start at the top where the source area is of that picture, you work your way down. We have a couple industrial properties, and then we, Dan, if you're handing the laser, that might be a good time to use it here. Appreciate it. There's some rural homesteads immediately downstream from that. We have one subdivision south of that, and then we have a forested undeveloped tracts that are below that. So as you can tell, we had a lot of different types of properties we had to deal with, a lot of different types of property owners we had to work with. And in between, we also had the community with regard to right-of-ways and that kind of thing along the roadway. Moving over to the remedial timeline, the site was impacted from historical disposal practices in the mid-1960s. There was a couple of disposal areas, fairly large disposal areas that were excavated in 1999. And in 2001, a groundwater recovery system was installed along the property line to keep the groundwater contamination from migrating off-site. Later investigations, we're talking after the recovery system was put in place, determined that the plume extended a lot farther than was predicted. In fact, it extended a distance. In 2006, we determined 4,000 feet down gradient from the source area. In 2006, we actually installed a mid-plume containment system, a recovery system that to keep the plume from further advance. And then we evaluated different technologies and determined that enhanced anaerobic bioremediation, a pilot test determined that that would be the most effective technology to address this plume. And we got agency approval in 2011. We phased it because different areas of the property had different requirements. And so I'll get into that as we progress through this presentation. And then in 2020, the source area residual mass was characterized, and we evaluated a number of different solutions for that, and Dan will cover that later. Next. A little history on the geology, or a little description of the geology on the site. The transmissive zone is primarily between 20 to 45 feet. There's a fairly thin middle clay unit that is encountered at about 65 feet in the source area. And as you move down gradient, we see it around 80 feet below grade. And then there's a really thick clay layer that is very protective of there's actually a drinking water aquifer that's underneath it, but it's three of the property owners had private wells, and those wells were sampled as well, and none of them ever detected any 1,2 DCA. Next. This figure shows a distribution. This is from 2008. Shows the depiction of where the plume was extending. And as you can see, the highest 1,2 DCA levels were measured in groundwater immediately above the thin clay layer in the source area, right around 65 feet. And this also does a really good job of showing the actual thin intermediate clay or layer as it worked its way down plume. Middle clay units about 65 in the source area, and has encountered around 80 towards the toe. It's also important to note that the 1,2 DCA tended to migrate down gradient in a relatively minor band between 25 and 45 feet. Next. So calling this a holistic remedy for 1,2 DCA, and I think when I looked up the definition of holistic, it's defined as parts that are being interconnected, and I think that's a pretty good description of what we had to do on this site. We had to do a number of different things depending on timing, depending on a lot of different variables, and depending on what made the most sense for that various portion of the site. In the source area, we had targeted vadose zone mass removal, the excavation, followed by containment at the property line. And subsequently, in 2020, we actually did characterization and came up with some conceptual ideas for dealing with that source plume. Down gradient, we had a hydraulic containment at the mid plume in 2006 that was very successful at stalling the plume from further advance, and that gave us time to get to roll out our enhanced anaerobic bioremediation transects along the dilute plume. Next. So here's pictures of the excavation. I just want to point out that the excavation was extended from the pits, and the contamination extended all the way to the top of the groundwater, wherever the waste pits were located, which was about 22 to 23 feet below the ground surface. Next. As I mentioned, we installed two groundwater recovery systems at the site. The one on the left is the source area along the property line, and the one on the right is the one we installed mid-plume. It's important to note the one that we put on and the reason this is important to note, you'll see the little split in the plume and the diagram in the middle. The one on the left discharged into a nearby stormwater channel after the treated groundwater was discharged there. The treated groundwater on the right was discharged into an infiltration trench, and that clean water combined with the recovery operations tended to give you a lot of dilute groundwater in between where you see the plume kind of split. Next. So the goal when working with the agency was to achieve groundwater cleanup outside of the source area within 15 years. That's basically down gradient. And this was in 2011 when we started that. So the implementation was divided into 5 phases based on the property access and modeling predictions. We did pilot testing in 2009, and the pilot testing demonstrated that substrate pH buffer, something I should have mentioned earlier, the groundwater levels, the pH levels in the groundwater here, they hover around pH 6. And so the pH buffer is a necessary component to our mixture. And we included a microbial culture that was acclimated to work on 1,2 DCA. And the pilot study demonstrated we were able to achieve 60% reduction down gradient, and that was a 12-month study. And we saw that the effectiveness extended as much as 60 feet down gradient. All 5 phases of the enhanced bio were on private property. They required quite a bit of negotiation and a lot of coordination with the property owners. Priority was given to areas of the plume that, based on the modeling, predicted it would persist the longest. And injections were implemented using both injection wells and direct push injections, depending on property owner preferences and negotiated agreements. And we'll get into a little bit of that as we get into each of the different phases. The initial injection design was based on a 2-year travel time between transects, but we implemented a little more enhanced spacing to accommodate client and property owner timelines. The 2-year travel time was pretty. One of the things that we discovered as we were investigating this site, and the pilot study sort of proved it out, was the 2-year. The groundwater is fairly consistently moving about 100 feet per year, the velocity of the groundwater in this area. So that, I think that was a key to helping us work on this plume. The other thing I probably isn't reflected necessarily, but the maximum width of the plume is a fairly narrow plume. So it extends 4,000 feet long, but it was at its widest point, it was probably only about 150 to 160 feet wide, and generally it was less than 120 feet wide. We conducted performance monitoring semi-annually initially, just to monitor the performance of the transects, determine how long the transects were the injection amendments that we added were going to last. And we conducted some refresh events in 2008 and 2018 and 2019 in a handful of the transects to supplement the treatment. Next. This slide provides just sort of a picture of the injection process and our reactive barrier walls, basically our passive barrier walls. So we are injecting into flush mount wells and direct push or above grade wells, and by direct push technology. We actually used above grade wells when we were in areas like the forest and stuff like that, where we had a hard time finding the wells. But we would inject it into the wells. The plume, as it migrates along, is traveling through the area that we added the amendments. Dairy whey and soy oil were the food grade materials that we added in, along with our pH buffer. With regard to the injection wells, we would come back about 3 months later after the groundwater had acclimated and added our culture acclimated to the grade 1,2 DCA. And with regard to the DPTs, we actually would create our injectate. We would create an anaerobic injectate using the site's groundwater, and then we would add our culture to that and include it during our injection. Next. So phases were numbered based on what we anticipated the order of completion, but as you'll discover, I'm going to walk through them chronologically, not necessarily by their phase number. But the actual implementation was dictated by the property owner's coordination. So phase 1 is in the center of the property where Dan has the laser, and that was a private residence. Phase 2 was along this right-of-ways of the road and in this residential neighborhood, just immediately down gradient. Phase 5 was the next step. It was the most down gradient towards the toe of the plume. And a lot of the reason that got accelerated too was because that private property owner was considering developing the property and wanted us to try to get out there and put the stuff where we wanted it, so that way he could avoid developing where we were putting our wells. Phase 4 was closest to the source area. That's the next one we went up. It's immediately down grading from the source area. And then in phase 3 was the last one we got to. So next. It's a little clearer, a little closer up picture of phase 1 and 2. As you can see, the little triangles at the top are the direct push. The resident, their home is right at the very top of that little square. Did not want our injection wells close by. The injection wells he allowed us to put in are actually surrounded by a bunch of trees and woods and along the property line and the right of way. And so we were able to put injection wells and negotiate injection wells along the right of way and in the wooded portions towards the front of his property. We also negotiated and had to get permits from the city or the county to install in the right of way on the other side of the street and also in the center of the neighborhood. So that's phase 1 and 2. Next. We have some pictures of phase 1 and 2. So the picture on the left is you can see the home in the background. And this is the actual phase 1 direct push injections. The one on the right gives you a picture of injection on the residential street in the neighborhood we were at. And the county would not let us put it in the road, so we were actually putting it in their yards. We did disguise them so they look like the wells that our injection wells we put in look like they're the irrigation wells you might see in most yards as far as the irrigation manholes. Next. Phase 5 is where we proceeded next, and that was to address the plume towards the edge of the plume. And this was solely injection wells, and these are solely above grade because they're in the forested area. The distance between the initial transects was based on 2-year travel time initially. And then we conducted a refresh event in 2018. And at the time of that refresh event, we also did an expansion or an enhancement of our treatment. We tightened our transects to 100-foot based on the data that we were seeing from our performance wells. And so we used a lot of that information to target areas where in the core of the plume where it appeared to be persisting. So we wouldn't have to wait the 2-year travel time. We wanted to make sure we were being more aggressive at it. And we also put a transect at the very toe of the plume at the request of the client because he wanted a little added protection to make sure there was no further migration. And this coincided with the decision to discontinue operating the mid-plume recovery system. Move to the next, please. Next. Yep. Okay, so this just shows a picture. This is the wooded area, just to give you a perspective. Oh, sorry, I think you went too far. This just to give you perspective of the forested area. There was a service road back there, but as you can imagine, the service road didn't go east and west. It only went north and south, and so we had to create our own paths a little bit back in the woods. And there were some pretty tight conditions and some tight maneuvering. Next. So phase 4, we had a unique situation with a stagnant portion of the plume caused by operation of the source area recovery system. If you want to use the laser, Dan, it's kind of showing the southern end. You can kind of see where the stagnant area is. We got that little lobe there to the left or whatever. But what we were looking at, we had a little stagnant area there that the modeling indicated would be there. And when we were putting wells in and looking at the hydraulic gradients and some of our data, it was confirming that we would have to do something a little more aggressive to get that area to clean itself up, or it was going to take way too long to clean. So what we installed was, you see the horizontal injection trenches being installed on the right, or on the left, in the picture on the left. And you can see the blue line on the figure shows the location of those injection trenches. So the plan was to take the treated groundwater from the source area recovery system, install them and inject it into these infiltration trenches, and that would help alleviate the stagnant zone by pushing water back towards the recovery system and through our permeable reactive barrier that we installed. And it would also assist us with the phase 3, which I haven't really discussed about, but that was one of our concerns, was making sure we could get the velocity back to a normal flow across the phase 3 property, so that we'd get effective treatment on that phase as well. Next. So phase 3 was located immediately down gradient of phase 4, and it was our most recalcitrant property owner. We thought we'd get to them sooner, but as you can tell, in 2019, when we finally negotiated the agreement to get out there, and he did not want any additional wells. He had some wells to monitor the plume on his property, but he didn't want any other wells sticking up. And so he allowed us to come in with DPT injections, and to and he only allowed us one-time access. So the access agreement that was signed with him only allowed us to get out there once. So we significantly tightened the distance between the wells. We also modified the injectate design, and we did it all with the intention of making sure, trying to hedge our bets that this more aggressive tactic on his property was going to achieve the goals within 5 years. Next. So how did we do? The picture on the left is 2007. This was after we just finished our determination of the plume extent, our investigation of how far the plume went. We had already installed the mid-plume containment system right in the wooded area. It's actually down a little bit farther, Dan. A little farther. That's kind of at the bottom of it. Yeah, right about that area. So that's where we installed it. And you can see the effects of the injecting, not only recovering the groundwater with the contaminants in it, but also re-injecting the clean water, which was obviously assisting to provide a little bit of dilution and cutting off the plume. The next picture over, you see the split in the middle, plume extent October 2010. This is before we started doing any enhanced bio work whatsoever. And what you can see there is the result of, we didn't have a whole lot of data points, but we also, this is where he has the laser is where we did the pilot test. And so our pilot test was done in 2009. And so it shows the effectiveness of the pilot test clearly cutting off the plume at that point. The pilot, later data suggested, if you look over the picture on the right, that the plume extend a little wider than we showed in that picture, the one in the middle, but at the time that was all the data we had, and so that's why we showed it the way it was. The other thing that's really hard, and I apologize for that, the thing that's kind of hard to see in this picture is if you go to the one on the left, the middle contours are 100 parts per billion of 1,2-DCA. And as you move to the 2010, you still see the 100 parts per billion, the ones in the very center. And up top too as well in the source area. But as you move over to the one after we did the EAB, not only are we seeing the plume narrow, we're also seeing that what you have here is a 5 and a 10 part per billion. So what we had is we're down to a couple places that were above 10 parts per billion, and most of the places are actually, below 10 part per billion, approaching the actual groundwater standard for the site. We had a little persistent guide down here that was, I think, maybe about 25 parts per billion, which is what we targeted with the phase 5 enhance that we were doing. And so I think clearly the enhanced bios had a very positive effect on helping us achieve our goal for the site. Next. So the down gradient plume remedy results, the goal is within reach 10 years after we initiated the EAB in 2012. The integrated approach is achieving its goals while we're respecting the offsite property owners. In 1999, the excavation removed the bulk of the shallow contaminant mass. However, it left quite a bit remaining in the groundwater. A recovery system was installed in 2001, prevented migration from further migration from down from the source area. Investigations in 2005 determined the 1,2-DCA plume extended much farther, so we installed the mid-plume recovery system to stop further advancement. The enhanced bio was installed in phases to enable implementation and to optimize the results from prior phases to help meet objectives while accommodating stakeholder interests. And the performance monitoring enabled timely determination of groundwater conditions and the need to refresh portions of each transect as the substrate was depleted. Next. So the remedy performance, hydraulic containment enhanced bioremediation of the passive barriers. We were able to contain the source at contain the source area mass at the source area. We were able to reduce the 1,2-DCA levels under offsite properties. In fact, within 7 years, 10 offsite properties that were previously affected were no longer affected. And the requirement that the agency was imposed on us initially for a response action plan was to achieve cleanup within 15 years, and we're certainly on target to do that. The collapsed offsite plume, dilute plume, and reduced plume footprint by at least 50%. And the mid-plume pumping system was turned off in 2018. The source area pumping system was retained to prevent source mass migration. And just a couple points on that before I hand it off over to Dan. When we did that optimization, what we were doing is we right-sized the stripper from the 2001 stripper that was installed to get a much more, so it'd be more sized appropriately and to be much more energy efficient. It was automated so that we could do remote operation and monitoring. And we also did some adjustments of the well locations to more effectively capture the plume. And one of the key things we did in 2018 when we did that optimization was we tied the discharge of the treated groundwater from discharging to the nearby surface channel into the infiltration trenches that were installed as part of the Phase 4 EAB. So I think that's it for me, Dan. I'll pass it over to you.
All right, thanks, Brian. So I think a key that we see here is that when we started on this project, we sat down with our client and our regulatory agencies and really prioritized how we were going to attack the site and the dilute plume. And the priorities were first to stop additional plume migration. That was the reasoning for the two capture systems that we implemented. And then to address the dilute plume that was impacting groundwater beneath private properties. And Brian did a nice job of presenting how the EAB PRBs were installed, the performance that we were able to achieve, and the eventual collapse of that dilute plume off-site, and the restoration of groundwater quality beneath those private properties. The third priority was essentially once we were able to address the dilute plume, we wanted to return to the source area to identify a better solution for the residual source mass. And we started in 2008-9 with some sampling in the source area in conjunction with the dilute plume investigation. And through that limited sampling that we did in the source area, we were able to identify that there were elevated concentrations of 1,2-DCA in the source area, and they increased with vertical depth. So as you move downward through the A-zone sand and you approach the AB aquitard, that thin clay lens that Brian talked about in the cross section, 1,2-DCA concentrations increased in the source area. So based upon that historical data that was collected, in the 2008-2009 timeframe, we were able to demonstrate that the residual source mass was really at the bottom of the A zone. We saw some indication that there were some inner A zone limited extent clay lenses that were also impacted by higher concentrations of 1,2-DCA, but the bulk of the remaining mass was down at the bottom of the A zone and in the top of that AB aquitard. And here's just a cross section that we prepared in 2008 based upon that limited sampling, and it just shows graphically what we found: high concentrations at the bottom of the A zone, and based upon the data that we collected, up around maybe 1 milligram per liter towards the bottom of the A zone, top of the aquitard, and maybe about half that, 500 micrograms per liter, in the inner A zone clays, shown here in the middle in the cross section. So with that basis to start with, we developed a series of objectives for a high resolution site characterization project that we implemented in the source zone property. First, we started with the data we had and the conceptual model that we had developed from the 2008-9 groundwater grab sampling event. And then we built off that by driving a series of borings, vertical profiles using membrane interface probe to further define in three-dimensional space where that remaining mass was. And then we wanted to use that better understanding of where mass remained to evaluate potential remedial options for that residual mass, and then to cost and compare the application of a more aggressive approach for the source area to continuing to operate that pump and treat system that was on the property line that had already been in place. And the idea was to develop a means to understand better where the mass was, how much it would cost to address that mass in whatever form we developed, and then to see if that more aggressive approach was more cost effective or the same or less cost effective to just continuing to operate the capture system at the property line. And this slide just shows an example of a vertical profile that we collected using membrane interface probe. And on the left, you see electron or EC, which is electrical conductivity and an indication of soil stratigraphy. And then moving from left to right, you have your PID, your FID, your hydraulic profiling tool pressure, which is again is an indication of stratigraphy. And then on the right hand profile, you see the advanced electron capture detector, which is specific to chlorinated solvents. And in this case, 1,2-DCA is the only chlorinated solvent present. So it's directly indicative of 1,2-DCA concentration. And you can see in the stratigraphy, the top clay in the EC trace, as well as the HPT trace. Then you get into the A zone sand, where electrical conductivity and injection pressure or hydraulic profiling tool pressure drops off. There are a few inner A silty clay lenses down here around 40 feet is one example of that. And then you get down towards the bottom and you start transitioning into the aquitard. Your hydraulic profiling tool pressure increases significantly, indicating a clay. Electrical conductivity does the same thing. So a great confirmation of where that aquitard is. And lo and behold, you see peaks in the XSD, which is again indicative of 1,2-DCA concentrations at the bottom of the A zone sand, which is really kind of transitioning into more of a silty fine sand, sandy silt at this point, and then down into the aquitard itself. And these concentrations or these peaks are indicative of concentrations in the range of, about 1 milligram per liter 1,2-DCA. And after we completed our MIP work, we drove a total of, I think, 19 MIP locations. We confirmed our understanding of vertical distribution of 1,2-DCA with some grab sampling. And each of these boxes in the map on the right are grab sample locations and the vertical intervals that were collected. And then you see the data set in the center of the slide where you see, in most cases, the highest concentrations at the bottom of the boring. So for example, at AGC4, which is located right here on the east side, you have a peak concentration at about 60 feet of 590 micrograms per liter of 1,2-DCA. Max concentration we detected during this grab sampling event was about 800 micrograms per liter. So we took the MIP data as we collected it and the historical 2008-2009 data, and we built a three-dimensional stratigraphic and contaminant condition model so that we could better understand in 3 dimensions and visually, graphically, where that mass remained. And as we collected more data, additional MIP points or additional grab samples, we added it to our site conceptual model so that this site conceptual model could be used in the field to guide placement of future points and also as a communications tool for our client and ultimately our agency representatives. And on this graphic, the low permeability soils are shown in brown. So this brown polygon on the top is the top clay. The transparent interval in the middle is the A zone sand. So you see a few inter-A zone clays of limited horizontal extent here and there that were mapped using the MIP and boring logs. And then you get down into the AB aquitard at the bottom, this brown color with the 1,2-DCA blob sitting on top. So some of the findings, we found residual 1,2-DCA mass in an area that was about 180 by 200 feet, so a relatively small size. And it was limited vertically to the top of the AB aquitard and the bottom of that A zone sand. So the impacted zone was 2 to 8 feet thick vertically and about 180 by 200 feet laterally, so relatively limited. We saw concentrations as high as about 1 milligram per liter of 1,2-DCA in the MIP work, the XSD response, which is an estimated response, and the grab sampling. And if you remember back to the 2008 data I presented early on, concentrations were very similar, which allows you to at least conceptually conclude that in 10 years of what was essentially natural attenuation, concentrations didn't decline much in the source area soils or in the source area groundwater. Just an added point, the AB aquitard is relatively thin. At its thickest, it's maybe 5 to 8 feet thick, and then it thins to maybe 1 to 2 feet thick on the east side of the property line. But we were lucky, at least stratigraphically, in that in the areas where it's relatively thin, 1,2-DCA concentrations are relatively low. The B-zone sand in all of our sampling and the wells that are installed in the B-zone sand is unimpacted. So in terms of starting to think about remedy for this residual source mass, we identified 2 areas where we might apply remedy. One is the discharge zone, which is on the property line to the east side, and the second is the residual source mass zone shown in these colored polygons, and I'll explain what these are in a minute. And as we were starting to formulate our impacted areas or zones, we were also thinking about what the remedial goals might be for those zones. And, obviously for the discharge zone, the idea is to prevent unacceptable 1,2-DCA mass flux across the property line so that this residual mass did not result in the reformation of the dilute plume. And in the residual mass zone, again, this blue-green polygon, the objective was to accelerate degradation of that 1,2-DCA mass and to reduce the potential for mass flux from those impacted low permeability soils into the higher permeability soils, which would then migrate towards the property line. And we also wanted to make sure that we were addressing any potential risk associated with land use on the source area property while we address this remaining mass in terms of potential vapor intrusion if a building were to be built, protecting site workers that were working on site, either utility or investigation workers, and preventing groundwater usage while impacts to the source area groundwater remained. So in terms of solution, the source zone solution clearly was going to be one of 2 things. It was going to be a solution to reduce that mass, either directly through destruction or indirectly through a long-term biological destruction means, or second, to reduce the potential for that source mass to migrate out of the fine-grained soils and into the more permeable soils so that it could migrate. So 2 potential approaches, but ultimately the idea was to either encapsulate or destroy this remaining mass. In the discharge zone, clearly the remedy objective is to prevent migration across the property line, either through hydraulic control, which is what a pump and treat system is, or through destruction with like a permeable reactive barrier. And the thought was that if we could apply a remedy within the source zone to either destroy or encapsulate or immobilize that remaining mass, then the property line or discharge solution only has to last 5 to 8 years, which is the time it would take to rinse out the high permeability soils and watch concentrations decline along the property line. So some of the technology we looked at, of course, pump and treat. We looked at pump and treat on the property line as the base case or the comparison case for all of our potential remedial options. We looked at additional pump and treat in the residual source mass area as a means to hydraulically control and remove some of that mass. We retained it because pump and treat worked okay for the property line and for that mid-plume system that Brian talked about. We also looked at monitored natural attenuation, which clearly is effective on this site. The 1,2-DCA was slowly degrading over time, but ultimately we rejected it because the life expectancy or time scale for monitored natural attenuation is very long. We also looked at reactive metals. Zero valent iron was a relatively easy one to eliminate because it's been shown to be ineffective for 1,2-DCA. But zero valent zinc has been shown to be effective. We ultimately eliminated ZVZ because it's extremely expensive and has a very short reactivity lifespan or life scale. And compared to some of the other options, it's just not a cost-effective solution. Chemox is another great example where it's shown to be effective for 1,2-DCA, but it's very difficult to apply in low perm soils. And honestly, we had better solutions, so we eliminated it from consideration. Phytoremediation we kept because it's a very effective hydraulic means of hydraulic control using trees instead of electric pumps. And with the advent of the tree well technology, it's quite effective. And finally, enhanced bio, of course, we kept because we demonstrated it to be very effective for the dilute plume. Enhanced aerobic bioremediation we considered. There is some literature out there indicating that 1,2-DCA and contaminants like it, 1,4-dioxane as example, can be effectively degraded aerobically. But in this case, natural geochemistry is borderline into anaerobic. We already demonstrated that anaerobic is very successful on the site, so we eliminated it. And finally, in situ solidification, great potential technology that could be applied. And we retained it, at least for the source area, not for the property line or the discharge point. So some of our leading candidates, of course, EAB. We showed EAP works very well on the dilute plume, so we retained it for both the property line in the form of a permeable reactive barrier, and also for the source area as a source area application to degrade that residual mass. We retained deep soil mixing, at least as a cost comparison point, and we looked at targeted pump and treat. On the property line, EAB, of course, under PRB, I already mentioned. We also looked at phytoremediation in the form of tree wells, and of course, our base case of maintaining the pump and treat system. So some of our conclusions, and this is conclusions for both the source area work and the work that Brian presented, we demonstrated that enhanced bioremediation can be very effective for 1,2-DCA. In the dilute plume, certainly, in the plume cores up to a couple hundred micrograms per liter 1,2-DCA concentration, can very easily degrade that and achieve regulatory limits, 5 ppb, in a relatively short period of time. And we were achieving regulatory limits within 7 years for the dilute plume. But the low-cost solutions that we came up with for the dilute plumes were great. But enhanced bio is a low-cost solution for the source area as well, except that if that residual source mass is not addressed, even low-cost solutions aren't necessarily low cost because your time frame is extremely long. Membrane interface probe works really well for source area characterization for chlorinated solvents in general, fuels as well. We've demonstrated that it's very successful for less chlorinated molecules like 1,2-DCA, would also be effective for 1,2-DCE as well. And using the calibration methodologies that we applied in the field, we were seeing 1,2-DCA concentrations down to the 40 to 50 part per billion range. So it's very effective and works great. Now, high resolution site characterization is not cheap. There was a significant cost to even this small investigation, but based upon our cost estimating for the full scale applications, there's at least a 4x savings in reducing remedy footprints and optimizing full-scale remedy that offsets by far the high-resolution site characterization investigation costs. And in some cases, we've seen that offset as great as 10x, 12x, where we are able to significantly optimize the remedy based upon the high-resolution site characterization results. And a strategic approach, including the identification and location of those residual source mass impacts, will ultimately be the lowest cost. The ideal remedy is a low-cost solution for the dilute plume, so you're addressing all of those impacts, but also the addressment of the residual source mass so that your life scale for your site is reduced to something that is manageable, decades instead of maybe 100 years or more. And there's a lot of sites out there. I mean, I've been in this business for 26 years. Some of the sites that I worked on initially that were closed with M&A and long-term monitoring, you might consider a reapproach and use high resolution site characterization to characterize your source area, identify where the residual mass is that's continuing to fuel your dilute plumes, and address that residual mass so that you can reduce your site life scale and thus reduce your future long-term cost and ultimately liability. And one conclusion I wanted to add to this is that Brian talked about it during the dilute plume applications. I didn't talk about it a whole lot in the source area, but a key to our success, and kind of a secret key to our success on this site, was really strong communication between us and our client and our regulatory agencies. But for the dilute plume work, strong communication, transparency, and really willing to work with the property owners to ensure that we were applying an approach that was going to work, but also an approach that was acceptable to the residents. And that's what I have. I think we have a little bit of time left for questions.
Yeah, thank you, Brian and Dan. That was a great presentation on a very complex site with a lot of hurdles that you had to navigate to successfully implement the remediation. If there's any questions, you can either raise your hands and we'll call on you, or you can enter your question into the chat as well. It looks like we have a couple questions already in the chat. So we'll start with Ray DeAllender asked, county roads often have county ownership extending into the yards. Were you actually outside of county property or just out of the pavement in the storm drain area?
Yeah, Ray, as I mentioned, the county pushed us into the yards because each of the yards has the 5-foot right of way. And they did not want it in the road because that would require them to have to do some work on it. They wanted us to do it in the yard. I don't know if that answers your question.
Yeah, basically, it sounds like you were still in the county property, just not trashing the road.
Yeah, well, each residential home has actually, there's a utility right away in the first 5 feet from the road. And so that's where the county has the right to go in and do stuff. And that's why they kicked us into that.
Yes,
Yeah.
yes.
Yeah.
That was my question. I've got
Yeah.
a 20-foot right away on my property like that, or
Yeah.
on my yard. So.
Yeah.
I see Jeffrey Graveson has his hand raised. You could go ahead and unmute yourself and ask your question.
Hi, yeah, this is Jeff. My question was more along the tree line. I worked on a phyto remediation project that you mentioned in California, and we used eucalyptus, and we had to get special permits because those are invasive species in California. And I was wondering about the trees that you planted, what variety they were, and were they different than the normal trees in the forest?
Yeah, I mean, Texas has similar issues in terms of invasive species. We didn't actually plant trees. We just looked at the trees that we would plant. We did look at eucalyptus for its amazing ability to extract a lot of water, but same issue. It's an invasive species for Texas. So we also looked at willow, which is a native species. And willows are great. They grow really fast. They extract a lot of water, not quite as good as eucalyptus. But if we were to plant trees along the property line, they would likely be willow.
We have a few more questions that came in through the chat. Matthew Colbert asked, how did you manage your relationships with the various property owners? Did any properties change hands during the project?
Yeah, great question. So transparency, we started with a public meeting where we rented a public space and brought in poster boards and invited the residents in to talk and ask any questions. So that was really the starting point. And then during application, or prior to application start, we visited all of the property owners, hand delivered a letter to them explaining what we wanted to do, and then basically stood on a doorstep and answered any questions they might have had. And then during application, if we planned to be on a property owner's property within the next couple of days, we would always visit, make sure that they understood when we were going to be there, what we were going to be doing, where we were going to be on their property, front yard or backyard, and they were kept fully aware. We also gave them the opportunity to help us adjust the locations. If our planned location was in the middle of their driveway and they wanted to set it off a little bit into their lawn, we gave them the flexibility to do that, and we just really involved them from start to finish. There were some properties that changed hands during the course of the remedy. So when an impacted property changes hands, of course the seller has to disclose to the buyer all of the stuff that's going on. So we did have that issue. Brian, I don't know if you wanted to add anything to that.
No, we just said there was the forested area downstream did have changed hands multiple times. And they actually had brought a developer. So we were actually working with their developer and had several meetings with them. And so that's helped facilitate some of our work down on the downgrading portion, the toe of the plume.
We have another question from Justin King. Have you estimated how long the residual mass in the source area would continue to feed the more transmissive zones where the dissolved plume could continue to migrate off-site? Or when would hydraulic containment no longer be needed to prevent off-site migration?
Yeah, that's a great question. And really the leading question for how long the life cycle actually is for a M&A and containment solution. We did model, estimate through modeling the expected life cycle of the residual mass with no application in the source area. The model estimated it about 80 years. I think it was actually 87, if I remember correctly. And then we estimated based on the destructive performance of enhanced bio, how much we thought we could reduce that. The modeling indicated that with an application of enhanced bio, we're looking at more like 20 to 25 years. But with the application of enhanced bio in the source area, not only would we be accelerating the destruction of the residual mass, which reduces the overall life cycle of the site, but we'd also be reducing or eliminating mass flux from the fine grain units into the more permeable units and reducing or eliminating that mass flux towards the property line directly, which would eliminate the need for the property line amendment altogether, whether it's pump and treat or PRB or what have you.
Okay, great. Next question is from Carrie Crozier. Was there any risk of indoor air, indoor air or vapor intrusion from having 1,2 DCA under residential areas?
Yeah, there was a couple times there were studies were performed looking at some modeling or whatever at the concentrations that would become a problem for indoor air inhalation under the residential neighborhood, and looking at it conservatively, even not assuming that there's about a 10 to 15 foot clay layer, surface clay layer. The assumption was what would the concentrations be if there was basically a loamy or soil type thing, and it was 10 times. Concentrations could be 10 times before they become an issue, 10 times what we are encountering in the groundwater. So that study was done once, and then the EPA changed their rules on us or how they do that. So we recalculated it the second time and came up with similar results.
I see Joseph Wall has his hand raised. If you want to unmute and ask your question, please go ahead.
Yes. Was there any health concerns that occurred in the residential area, and that was the reason why it was moved up in phase, or was there any health issues that occurred because of the 1,2 DCA?
No, I think the primary driver was when we modeled the plume, that was the area that we thought we needed to target. And it's also the easiest to access, actually, rather than the other ones. So we were able to get there based on the modeling results. If we were able to start pinching out the plume at that location, that was going to give us the most bang. Dan, you got any other thoughts on that? Or?
Yeah, I mean, the top clay was really the barrier to potential impacts to the homeowners. And none of the homeowners within the residential area had groundwater wells, irrigation, or drinking water. So it was really potential indoor air intrusion concern. But with that top clay, 20, 25 feet of dense clay between the ground surface and the impacted groundwater, there was very little risk associated with the dilute plume. We prioritize primarily based upon our modeling results, and we picked properties where the modeling results indicated that the plume would persist most. So we tackled phase 1 and 2 first because the model predicted that those areas would persist, or the 1,2 DCA beneath those areas would persist most.
Thank you.
We have a couple more questions in the chat. I see it's about the end of our presentation, but we'll try to get these two answered. And if anybody else has any more, you can either ask now, or you can always send our presenters an email later. From Megan Clark, how did you determine the velocity of the groundwater flow in the plume to determine appropriate spacing?
Great question. So two methodologies. One is just simply hydraulic connectivity and slope of the potentiometric surface, so a very simple calculation. Another is we had enough data to actually track the advancement of the plume toe for a short period of time during the investigation phase. So a combination of the two allowed us to calculate an estimated groundwater flow rate. And then we spaced our PRBs essentially using a conservative assumption of groundwater flow to give us a less than 2-year travel time between PRBs.
It's also, the pilot study also confirmed it for us as well. We saw the hit it nail on the head, actually.
Yeah, good point.
And then the last question is from Glenn Ulrich. What remedy are you leaning towards to address the source? Are you sure back diffusion from the underlying clay is not a source along the plume?
Yeah, great question. I'll take the first one first. I think enhanced bio is probably the most applicable in terms of just being able to apply it. We already have a ton of results demonstrating that the technology works, and we've optimized how to apply it on the site for this contaminant. And we also have performance data so that we can very accurately predict performance and life cycle and all that good stuff. In terms of the top clay as a secondary source, it may be, but based upon the performance monitoring data that we have through the life cycle of the dilute plume applications, we really didn't see like rebound of 1,2 DCA in PRB transects that hit depletion. We have a number of transects that were depleted at least 3 or 4 years ago at this point, and we're not seeing rebounds in 1,2 DCA concentrations, which leads me to believe that the top clay just didn't have enough 1,2 DCA mass absorbed into it to pose a problem into the future.
All right, well, I think that will wrap us up for today. If you want to go to the next slide. So our next webinar will be on February 8th at 12:30 Eastern. We presented by Dr. Jeffrey Evans on the state of the practice for vertical barriers for control of contaminant transport in the subsurface. So we really hope you can join us for that, which will be a very interesting presentation. A link to the PDH credit form has been posted. If you have any issues downloading that form, just please contact us and we can get it to you. And if you miss any portion of the webinar or just want to go back and review information, it will be posted on our YouTube channel in the next few days. So thank you again to everybody who joined us today for the webinar, and we hope to see you next month.